Okay, well, first, I'm gonna share with y'all why I emailed you and thought that I might not have class today. You'll find it interesting. Um, okay, so, um, as some of you may know, I traveled to California over spring break, fall break. I'd like to do it on spring break too, but, all right. And yesterday was when I was getting back here. And everything went smoothly, flying from out there to New Orleans. And then I needed to drive back, and that was going smoothly too, until I got to Mississippi. So I go to Mississippi, and you may know, like on I-59, there's a welcome center, rest area, and I pulled off there. And when I got out, I happened to look at the tire, driver's side front, and saw that it had a nasty sidewall bulge in it. And one should definitely not drive on a tire like that. It could blow at any time. Um, the security guard there offered to help put the spare tire on, which was very generous. He didn't have to do that, but it turned out he could not because whoever owned my car before I bought it used put some aftermarket wheels on it that have these specialized lug nuts that you need the right socket to remove, and nobody has that socket. It just doesn't exist, I'm pretty sure. And so he couldn't help with that. So I took my life in my hands and drove this car on this about to blow tire to Picayune, Walmart, and they couldn't help me either. And so I'd stay the night there, taking risk again to drive to the hotel, because there are no Uber or Lyft drivers in Picayune. At least, well, there are, but not at that hour. It was like 10 p.m. And this is after I walked over from the Picayune Walmart to their McDonald's, and then on the way back, thought I'd take a shortcut through what looked like a grassy field, but really was mud. And my shoes were submerged in mud. I could not see them. I had to reach down into the mud to pull them out. So probably a good thing I didn't get a Uber or Lyft driver, because it would have been upset at me messing up their car. So I took a chance again and drove to a hotel. Okay, following morning, back to Walmart, they still can't help me. Take it to a tire place, they put the spare on, no charge. Great, okay, I'm ready to go. Go get gas. They did not bother to check that the tire had enough air, the spare had enough air in it. These people make their living doing tires. You think they can check something as fundamental as that? They do this all the time. No. So, thankfully, I happened to check to avoid another brush of death. And got going again. All right, everything's fine. Get all the way up here. And because of my unfortunate shoe incident, I guess Megan can't see this, flip-flops that I happen to have in the car, fortunately. As I'm about to pull off onto 59 onto Hardy, my right flip-flop slips, and I had to think quick to like get it off me so that I could still use the gas and brake. So, and then finally, my odyssey will end soon because I got a new tire ordered. So, yeah, good times. So, so many things right in a row that just like a string of misfortunes and near misses, and yeah, I should be dead several times over. So I'm not traveling for a while.
So, were you alone or you traveled with your family?
Alone.
Oh, okay.
Yeah. So, Jeez. So,
Yeah.
yeah. I think I'm just cursed when it comes to tires. Bad things happen with them all the time. And I found that it even carries over to rental cars. Yeah, that doesn't have to be just my own. So, okay, now, Um, so our schedule's a little bit messed up, thanks to this university's insane prioritization of football above all. Because the original schedule I made for this week was to cover material today and Thursday, but now Thursday's gone. And the thing is, I already have more things lined up for next week, so that may put me in a position of having to cover more today than I thought or wanted. So I guess I could just give that a shot in spite of me just taking up some time in the story, but of course that was worth it. And we'll see how that goes. Now, I should ask, how's homework coming? Okay. Yeah. Okay. All right. Okay. So this part where you're trying to get fourth order by using a 5-point or 6-point stencil. Okay. So really, this problem is all about making the right A. And
Transformation on basically.
yeah.
Working with you.
Okay. Now, are you talking about the coding part or versus analysis?
Actually, I'm just trying to figure out the math.
Okay. Oh, like to get the finite difference rule, or
Yeah.
oh, instead of using the rule to get the coefficients. All right.
So, that's where I'm at it.
Okay. I mean, okay. Because if you're not using differential, or you're using differential, but again,
This is
but how you would do it if you weren't using differential is you'd set up a system of equations where you're trying to use u of x naught and x naught plus or minus h and plus or minus 2h. This is very interior rows.
the last term becomes h.
Yeah, now the thing is, since it's a second derivative and you're looking for fourth order accuracy, that means you really should take your Taylor expansion by that order h to a fourth term is going to show up with a sixth derivative.
That's what I have just written.
Yeah. And really you should take the expansion a little further than that, just so you can isolate that leading error term. Like if you take it out to the 7th degree, then.
Put you x on writing.
Yeah, okay. So, yeah, and then in this case, you're gonna have a system of 5 equations, 5 unknowns for the coefficients of because you're using 5 points. And because it's second derivative, there should be like a symmetry to the coefficients. Although, if you're not going to use differential, you can at least use backslash to solve a system of equations once you have it. Because, okay, now when you are, now if you set up a system of equations so that all the terms of the 0th, 1st, 3rd, and 4th derivative terms cancel out, and then and you get saved by itself. So that system of equations, you could, it of course will involve h, your spacing. But if you were to set h to 1, then you could take that, then your matrix would be numbers, you could solve it in MATLAB. And then you just divide all the coefficients by h squared. Okay. But that's for the interior rows. For the boundary rows.
Forward, I am inspired on.
Okay.
That's the first.
Okay.
I did the.
Oh, thank you.
I know how much you dislike it.
And anyway, right, it looks, it's like. That one's good. Yeah, the thing is, from a, back to the four-folder part, for the first and last rows, you again need four-folder accuracy, but you can't do a symmetric stencil anymore. So now you're gonna need 6 points.
Nice one.
Yeah, and then 1, 2, 3, 4. So then you have to solve a 6 by 6 system, so you're children expanding even more points.
Okay, that's what I was confused about, because this system is, let's see. This one we did not have a defined dimension initially, so I was kind of,
Okay. Yeah.
I'll see, maybe I'll do it another.
Okay. Yeah. But yeah, because yeah, the difference here is like because you need more points for higher order accuracy, can't use this one stencil all the way through. So in the general case, if you're taking a certain derivative and you want a certain order of accuracy, to get how many points you need, you end up adding those two numbers, order derivative and order of accuracy that you want. So fourth order accuracy, second derivative, you generally need 6 points. The exception is where you have symmetry, so you can get away with 1 less point. How's your homework coming?
Yeah, I mean, I submitted mine yesterday, but
Oh, Canvas did not notify me. Okay.
but I had issues with question 2B,
Okay.
the piecewise function
Oh, right. Okay.
with the coding. I was having that.
Okay. What happened?
How to get the approximate solutions.
Oh, okay. So you got
I did integrating everything. I had the
okay.
yes,
Yeah.
but how to get the approximate solution?
Okay. Well, if the approach would be the same as in the other case because you're just using the same matrix, different f. For a piecewise function.
Oh, okay.
Yeah.
How do you factor in the boundary condition? The first one, you have x is less or equal to half.
Okay, I'm gonna pull up the assignment here. Okay. Okay. Well, now while your solution has to satisfy the boundary conditions, F does not. Like, so really, all you're going to do is, for your, okay. So since f is supposed to be 1 for x less than or equal to a half, 0 otherwise, the easiest way to do this in MATLAB, so first you can set f equal to 0 vector of the right size. And then you can use logical indexing, and so I'm assuming that you have some column vector that can be set up this way for your x, your grid. So then you can do f x less than or equal to 1/2 is equal to 1, and that'll set the appropriate elements. Is it okay? So you don't need to do anything special with this problem in view of the boundary conditions compared to the other one. Okay. Now, something to keep in mind is, as you've seen from various Taylor expansions for error analysis of these schemes, the error term always involves a power of h and some higher order derivative of a solution. So with the standard center difference in second order stencil, the error term involves something order h squared times the fourth derivative of u, which is minus the second derivative of f. Now, problem with higher order schemes is they require higher order derivatives of a solution to exist, and what if they don't? So now, solutions of Poisson's equation ought to, solutions of Laplace's equation are always infinitely smooth. Poisson's equation, not necessarily, because f is not expected to be smooth. Because for keystones like minus uxx equals f, whatever degree of regularity f has, u will have regularity at least 2 greater, because anytime you integrate a function, it becomes smoother by 1 degree. So the consequence of that is you are not guaranteed to get the order of accuracy that you expect if the derivatives in the error formula do not exist. So if you're expecting, say, second order accuracy, fourth order accuracy, if you don't get it, that doesn't mean your code is wrong. Look at the problem. What derivative does the error formula require? Does that derivative exist? Here we have a discontinuous f. So things like that can create a problem. This is actually why there's some, including some colleagues of mine, that actually prefer to use low order schemes because they deal with problems where solutions are not necessarily smooth. And for a low order scheme, there's less of a regularity requirement. Because if you have if you're solving a problem where you have like discontinuous coefficients, maybe you have a discontinuous solution, and then you're going to use some fourth order scheme that requires 6 derivatives to exist, you're not getting fourth order accuracy. It's a waste of time to pursue it. But there's some people who really believe in that. So here's why I guess maybe that's why I do spectral methods, where problems are expected to have smooth solutions. So I don't think about that. So that answers your question there? Okay. Any other? Oh,
I want to know if there is a reason why we use the log plots instead of the regular plotting method.
it's because, so that way the, function you're plotting, or your error or power of h for comparison purposes will be a straight line. So that way it's easy to tell if, well, I guess if your error is like a constant times h to the p, and the and you could visually try to compare that way too, but with log it's easier to spot trends. Yeah. Any other homework questions? I guess that's a way of stalling because I'm not looking forward to covering all these notes. I mean,
Saying they are person,
what?
who end saying they're in.
Okay. Well, but again, I don't have a ton of material queued up for next week, so if I don't get through everything here. Okay. But one of the things I'm looking at here is conjugate gradient. It's always unfair to cover. But, we'll see how this goes. Okay. Okay. All right. You really stop messaging me. Okay.
Today because
Oh, people's phones going off?
it's abuse. I have a very, no, I have trouble of reading.
Oh boy.
I have my limit of points. First one out, and I gave them a minute to, summarize everything, go check that out. You hear me? And he was like, you know what? And now out.
Wow. You play hardball.
Get so tired.
Well, yeah. I always love stuff I hear about from your fellow GTAs, but let's like teach 101 or 101S. It's like, oh God, I'm so glad I'm not doing that because I would just like, yeah. One of them gave me attitude. Like, oh really? Oh, jeez. What? Okay. All right. I don't know if you know, because we have our other university in town, the William Carey University, and one of my former students, Amber Mooney, who's a professor there now, is working on starting a science student chapter there. So it will become, between ours and theirs, the only two science student chapters in all of Mississippi. And starting a chapter requires filling out a petition that's signed by current SIAM members. And so I know we got some help from having some student members here sign. But the petition got rejected because 4 of the people involved were not actually current SIAM members. Like they may be part of a chapter, but maybe they made their let their membership lapse. And we need to not have that happen, like especially if they happen to be like an officer in a chapter. So I'm wondering, like, okay, are any of those USM people? That's okay. Because he was asking like, are there any faculty, and actually we have a lot of applied math faculty here at USM, but they're not necessarily, some might be science members, but not really sure who, because for faculty, it's expensive to keep it up. It's like $170 or something a year to maintain our membership. Um, and it used to be that, if you're not part of a chapter and you're like a graduate student paying for a membership, it's not that much. It's like $30 or so a year. And then you would graduate, and then bam, you're paying the full rate right away, even if you might not have a great job yet. And it's because of me, as part of a focus group, that they instituted a transition. Like you start paying, so once you finish your PhD, you pay a little more each year. After 5 years, then you pay the full thing. So, so it's nice that my whining accomplished something. What? Oh, I know we still have one because Chandler is president of that too. Um, I don't know what they've been doing of late. Um, okay. All right. Um, right. Yeah, that's sorry, one second. Okay. All right. Now, um, people will stop messaging me. And, let's cover some. This is relevant to the last two homework problems. Well, no, wait, they're not the last two anymore. They're the last two that I have written up, problems 6 and 7, because there'll be one or two more problems to follow. Time-dependent problems, PDEs, that I'll start covering next week. Okay. Long last. Multigrid. um, Multigrid is a method that get to an algorithm. There's not very many steps to it, but students seem to have a hard time with coding it. Now that I've wasted nearly half the class, let's might even get from just one set of notes, let alone two. Okay, so so as usual, Poisson's equation plus equals f, and we have, this is based on my previous discussion of iterative methods, that this PDE becomes a system A equals F, like you're solving for homework. And the iteration you might use is this, have this form. Preconditioner P times the difference between your new iterates and your previous iterates is equal to the residual. When UK is your previous iterate, UK plus 1 is your new iterate. And I'm going to abbreviate this as RK, the residual. Now, this is not new. That was in a recent set of notes where an iterative method can be expressed as preconditioner times change in solution equals residual. Okay. Now, I've talked about certain preconditioners before, for example, preconditioners that lead to well-known stationary iterative methods like Jacobi and Gauss-Seidel and so forth. But I'm going to mention another one. P is equal to some multiple of identity, where delta t is some chosen time step. Now we're solving a time-independent PDE, so it seems strange to introduce a time step, but that's not as strange because if we consider a time-dependent PDE, we have a heat equation here I have a heat equation, and the steady state solution of this is where we just let du dt go to 0. So this goes out, and that's Poisson's equation. So even if we're solving Poisson's equation, we can think of it as the solution we get in the limit as time goes to infinity of this heat equation. Either way, you get to the same place, a solution of Poisson's equation. So you think in terms of like marching through time in a way using this preconditioner. Okay. Now, a property of using this preconditioner, first of all, it's not a great preconditioner in terms of convergence. The convergence is slow. But the error becomes smooth. Okay. So even though the error may not be going to 0 all that quickly, the high frequency components of the error are going to 0 rapidly. They're just leaving significant low frequency error behind. Okay. All right. Now, I should mention that the same behavior is true of other preconditioners that I mentioned previously. Jacobi. Gauss-Seidel. SOR. They also have this smoothing property. All right. Now, it's natural to ask, who cares? Because the whole goal is to make the error small and make it small quickly. Just because the error is smooth, if it's still going to 0 in a slow manner, do we really gain anything? And the answer is actually we do. Because with the error being smooth, we can represent a problem on a coarser grid. Okay. So if using one of these preconditioners has already given us pretty much the correct solution as far as high frequency components are concerned, only the low frequency components need to be corrected, then we can use a grid with fewer points, therefore greater efficiency. that is, or this right here is the essence of multigrid. That you start by solving a problem on a nice fine grid, the grid that you actually want to solve a problem on. You use some preconditioner like this one, or like Jacobi or Gauss-Seidel, a very simple method to implement. Each iteration is very quick. And you don't solve a problem all the way. You keep iterating until the high frequency components of the error are worn down, and then you move to a coarser grid. So you transfer the problem to that grid, and now, yeah, you keep going. You eliminate the highest frequency components of the error on this grid, and keep going until your grid gets so small that it's trivial. You're solving a one-by-one problem or something like that. And then you go back up your hierarchy. All right. Just don't type on my notes again. Um, all right. Any questions about what's going on here? All right. So now that I've given you the main idea behind multigrid, I'll describe the actual algorithm. So if you're solving a system like this, A equals F, that comes from some PDE such as Poisson equation. And that's really the focus. I'm going to describe the entire algorithm in reference to solving that system of equations, whatever PDE it comes from. Okay, so the system I'm going to solve is, okay, finding more typos here. All right. Now what I'm going to do in writing this system is I'm going to give subscripts of H for each of these entities to indicate the grid spacing, because that's going to vary since we're using multiple grids. Okay. And what I'm going to do is just show the interplay between two grids, one with spacing H and one with spacing 2H, to convey the idea of how multigrid works. Okay. So, first thing you do is use some preconditioner which we'll call P sub H. In other words, you're going to run a method such as Jacobi or Gauss-Seidel for a certain number of iterations, and that will give you an approximate solution we'll call UH. Right. So this is our initial approximation. You don't run this method all the way to convergence. You just carry out a few iterations. Okay. And the idea is, all you're trying to accomplish at this step is remove high frequency error. So we have a limited goal here. Okay. Now, once you do that, because the only error left is low frequency, we can move to a coarser grid. So, next step is to restrict the various entities that you have from a fine grid problem, KH and pH, to a coarser grid of spacing 2H. We're just going to double the spacing. Okay. Oh, sorry. Not just these two. Also, the residual. That's the most important part, actually. I didn't read far enough for my notes. The residual to a coarser grid. You mind the residual is right-hand side minus matrix times approximate solution. So you go ahead and compute that. But then what you do is you take your fine grid residual and you apply this matrix to it, a restriction matrix, capital RH, and the result is a residual defined on the coarser grid. That's why I'm using a subscript of 2H now. Oh. This requires a superscript also. So if it's a restriction operator, the subscript is the grid you're coming from. The superscript is the grid you're going to. So the process of restriction, that's why I've underlined and restrict. It's one of the most important terms for multigrid. Restriction is a process by which you transfer a function from the fine grid to a coarse grid. So this is actually going to be a rectangular matrix. More columns than rows. So it's short and wide. Now what you do is you solve the original problem on the coarse grid with a coarse grid version of your matrix. And your right-hand side is your coarse grid residual instead of the original right-hand side. And then the solution is your error, or at least an estimate of the error. So this should be the error. In your coarse grid solution. Then finally, the opposite of restrict, interpolate. With your error estimate, going back to the fine grid, so you take your coarse grid error and you multiply it by a matrix that does the opposite of capital R. It starts from a coarse grid, transfers to a fine grid. So just like this, the subscript is your starting point, the superscript is your ending point, and that gives you EH. So now so this is a matrix that has more rows than columns. Okay. And then you update. UH is equal to itself plus EH. Because you just estimated the error in your solution. So now you're adding the error in to get more accurate solution. You may recall I previously discussed a relationship between the error and the residual. A times the error equals residual. So we're using that here. And that's it. That's the whole process. But keep in mind, there's an implied recursion here. Because we're setting out initially to solve this problem. Well, this is a problem of the same form. So if we're writing like a MATLAB function whose job is to solve this problem for whatever right-hand side we're given, when we get down to this point, we just call that function again. The function can call itself. And this really weirds students out to an amazing degree. And it's understandable because it's kind of odd to have a function call itself. Because, and I think what takes time for students to grasp is that whenever a function is called, it has that call, the individual call to a function has its own separate memory space. So if I call this function to solve this, and it's doing all of these things, and it has its whatever variables your function has, then the function decides to call itself with these arguments, then that is happening independently. It does its thing. It comes back with the output, which is E2H in this case. And then, once this function call finishes, you pick up where you left off. And whatever variables you had here before you called this are still there. Yeah, and so that's, so I've seen every time I teach this class, the significant difficulty a lot of students have with wrapping their head around this notion of recursion. So it's just smart delegating. That saying, okay, go ahead. So this process between managing his algorithm says, okay, you go ahead and solve this. Come back to me with a solution, and I don't care how you get it. And then I work with it. And that just keeps filtering down through however many course grids you want to go through. And what you could do is at some point, since a grid each time has half as many points as before, so at some point the grid is so small that you don't need to continue doing this. You can just use backslash on a very small system. And then your error keeps bubbling all the way up. All right. So this is what so for problem 6 and 7, this is what you're putting in. This is what you're implementing. And this will be a call to that same function with the appropriate right-hand side. Yeah.
Add another recursion step to say course over. Does that affect the of the
Okay. I guess that'll depend on how well the high frequency error is disappearing. Like, so the assumption here is that if you look at the whole spectrum of low and high frequencies, your entire band, then you have what this algorithm is assuming is that the error in the higher half of frequencies has been reduced to an acceptable level. Now, if it turns out, in fact, that using its preconditioner eliminates error in like the upper 2/3 of frequencies, then sure, you can use free agent and it would work well. On the other hand, if you're not using its preconditioner to enough iterations and your significant error occupies more than half the frequencies, then even this won't work well. So that's why it's important to use the preconditioner enough to accommodate how much you're going to reduce the grid by. Interesting thought. Hadn't thought about that. So, kind of reminds me of how, because we all know that computers do everything in binary, but I'd heard about, I think it was in Russia a long time ago, the developed a computer that works in base 3. I'm not sure. Yeah, because I mean, the binary makes sense because you have, on and off. So I don't know how that translated into the electronics of it, like on, off, and yeah, like kinda on. I don't know. Yeah, I bring this up every time, and I think I should look that up, and I never do. So, okay. All right. Oh, these multigrid notes are almost done. Okay. I say, oh, I have 2 pages, but really it's a page plus epsilon. So. All right. Now, so part I've already mentioned. Now, one thing that you can do is, let's suppose you start some fine grid and you go down certain levels of coarsening, and then you get as coarse as you can, and then you start going back up. But maybe before you've resurfaced all the way and you've done this update at some mid-level grid, you could use this as some kind of initial guess to start this process all over again. And so there's been a lot of work on trying various cycles of grid coarsening and refining, because you have because what happens is, okay, so you start to define this grid, make it coarser, 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 and then that's as far as you can go, or as far as you want to go, and then you go back up here, and so now we're thinking of V, so like it's a V cycle. But at this point, you can decide, you know what, I'm going to use this as an initial guess of a solution for coarsening again from this point instead of going all the way back up. So that's called a W cycle. So these are things that researchers do. We just try all the letters, or letters that make sense. Okay, so there's a lot of flexibility in what you do as transitioning from one grid to another. Okay. All right, and there's also a variation called full multigrid, where you keep using increasingly deep V cycles. So like you come back to some point then like that.
A bit further.
Yeah.
A bit further.
Yeah. Okay. Now, the nice thing about this is, let's suppose you keep cutting the grid in half. So if your original problem is on an n-point grid, then you solve a problem on an n/2 point grid, an n/4, n/8, etc. You add all those up, and you get it adds up to 2n in the extreme. So all the work you did on all those coarser grids, however many there were, adds up to the same amount of work as on the original grid. It's like the infinitely many mathematicians walk into a bar joke, where you order a beer, half a beer, quarter of a beer, eighth of a beer, and then yeah, he puts 2 beers on the counter and says, "You guys got to know your limits." Yeah, so so that's why people like multigrid. It's so efficient that he can do all this work of refining so much and still not really expend very much because they're on coarser grids. Now, this is under the assumption that the amount of work per grid is linear in a number of points, but that is what we have for these kind of problems talking about, like what Poisson's equation. You're talking about sparse matrices. So the amount of work in solving an n by n system on a single grid is order n. And if you're cutting that amount of work in half by doubling the spacing, then that's what it works out to. So for relatively limited additional expense, you can gain a whole lot more in accuracy. Okay. Now, one thing I do not have in my notes, but I want to make sure it's at least in the homework hints, because I've mentioned these operators. A restriction interpolation operator, but I haven't said anything about what's actually involved with them. But I'm hoping I did in the homework hints. Okay. Oh. Okay. I need to fix this. It says restriction operator, interpolation operator are defined in the MIT notes. And also video for June 29th class. That was from back from 2017. Yeah. Okay. So what I'm going to do is, well, first, are there any questions about what we have here? Okay. That's probably often we're getting a problem anyway. So I guess these are problem 6 and 7, and you're on problem 2, 3. Okay, yeah. Well, I guess you got past problem 3. Yeah. Okay. Point is 6 and 7 are far away. Okay. Now, I'm taking a little risk here because I'm trying to do this from memory. But I actually don't have the entries of matrices I and R memorized, but just doing what makes sense from their function, restriction or interpolation. Okay, so matrix R that starts at a grid of spacing H and ends up on a grid of spacing 2H. So that's a matrix that has fewer rows than columns. The idea is it figures out the values of your function on the coarse grid by a weighted averaging of values from a finer grid. So this is going to have it's going to have n rows, or I guess n over 2 rows, and keep in mind that n, for these kind of problems, like usually boundary conditions, n is going to be a power of 2 minus 1. Okay. So I'll draw a picture of what's happening here. Get this right. So I'm going to use circles to indicate fine grid points. And I'm going to use X's to indicate coarse grid points. Okay. So the value at this first interior grid point, so we're looking at interior grid points, is we take 1/4 the value at this point, 1/2 plus 1/2 value at this point, plus 1/4 value at point to its right. And you see the weights all sum to 1. So there's a weighted averaging of these 3 function values to get the value right here. Similarly, to get the value at this second grid point, 1/4 of this value, 1/2 of this value, 1/4 of this value to the point right here. So now the number of okay, so if we have n grid points here, So for example, we have, like I said, a power of 2 minus 1, so maybe 31 grid points. Oh, okay, so n minus 1 over 2. And so that's how many rows it has. So this is a power of 2 minus 1, so is this. Okay. Yeah, so like 2 to the 4th minus 1, so 15. And this would be 7. All right. Now, so how we arrange it is we have 1/4 outside. So we have 1, 2, 1, 1, 2, 1, 1, 2, 1, and so on. It goes like that. That's the pattern of non-zero entries that pulls off this weighted averaging. So you can see this point is used to contribute to 2 coarse grid values. It's left and right neighbors. So that's the restriction matrix. The interpolation matrix. So what you do there is you're taking coarse grid values and you're basically like distributing them to fine grid values. So the way that this is going to work is we have okay. So like this point corresponds to a grid point that is in both the coarse and the fine grid. Like these points, where the x's are. So you just copy the value. Whereas for this point, this is a point that it corresponds to a grid point that is in the fine grid, but is not in the coarse grid. So you average 2 neighboring values. What?
The first one was only.
Oh, okay, here is a point that is in both grids. So you copy the value. So that's what the 1 is doing here. And you see that's happening for alternating points. These are grid points that are in the fine grid, but not the coarse grid. So you average neighboring values to get the fine grid point. Okay, now it turns out that there's a simple relationship between these 2 matrices. That the interpolation matrix for this kind of problem, for Poisson's equation, like 1 dimension, is equal to 2 times the restriction matrix transpose. So that part works out very nicely. So it really is, it's in your code, you can just make a restriction matrix. Be sure to make it a sparse matrix. And then just transpose and double it to get your interpolation one. All right, so now you have a lot of ingredients to do your multigrid problem when you get around to it. Any questions about how this matrix is set up? I guess as an example, so for this grid point right here, we take the average of these 2 values to get this one here. So linear interpolation in that case. All right. Well, I guess most of the time anyway. So, all right, I got some Multigrid stuff at least. So, all right, so then I'll figure out what I'm gonna do material wise for next time. Although, if need be, I could skip this next part. I don't know. Okay. So, we'll see. But yeah, because of football, no class Thursday. Oh yes, you're so glum, I'm sure. The face you made. I know, yeah. Yeah, I've only been to one game in the last seven. Oh yeah, absolutely, yeah. Pretty much, yeah. That is the message they're sending. So
I don't teach on to
okay, all right. Okay.
Yeah.
Alrighty. Well, I guess I'll see you in a week then. Oh, this Thursday? Oh. Army? No. Yeah, I mean, using that day to catch up on stuff. And I'm sure many of us are.